Let's try that again. Good morning. My name is David Ronca. I'm the manager of the Encoding Technologies team at Netflix. Just curious, was anybody here for my presentation last year, History of Netflix? Okay, I'm going to touch a little bit more history today, but today I'm going to be talking about the encoding and actually what our encoding workflow looks like. A little bit of where we came from, not so much history as much as where we are. A quick introduction. I think most everybody knows Netflix, but we started streaming in 2007 with an Internet Explorer plugin, hosting Windows Media Player, and we had about 2,000 titles today. We have award-winning originals, tens of millions of active devices, billions of hours of content streamed. We're international, and we just launched a 4K service in April. This is what our timeline looks like. Company was founded in 1997 as a DVD rental by mail service. 2000, we switched over to subscription model. In 2007, as I just mentioned, we added streaming. 2008 through 2010, this was my talk last year, was all about our device build out. Basically, all the devices all the work we did to get in all the devices, pretty much all the connected devices on the planet. 2010 was our first international launch in Canada, followed up in 11 with Latin America, 12 UK, and the Nordics, and more recently Norway, and then again, I'm chopped off here, UHD in 2014. Things I'm going to be talking about today, I'm going to give a very brief historical look at our encoding workflows. I'm going to talk about robust and scalable encoding in the cloud, our 4K solution, the Netflix source format roadmap. And first, I just want to review streaming profiles. For everybody who was here last year, this is one of my last slides. These are the profiles that we're producing in production for the various clients, both legacy and current. What we call CE1 is muxed ASF, WMA VC1 using WMDRM. CE2 is our first adaptive streaming. It's the same profile, it's just unmuxed, WMA VC1, WMDRM. CE3 is fragmented MP4 dash, and that is H.264 video with AAC, Dolby Digital, and Ogg Vorbis audio. But he's wondering about Ogg Vorbis, that's for the Wii, where MIPS are a little short, and that was about the best we could do. iOS 1 is muxed MPEG-2 transport stream to the HTTP live streaming specification. It's actually the same in codes as CE3, it's just muxed different. iOS 2 is unmuxed MPEG-2 transport stream, again to the HTTP live streaming specification, and again it's the same in codes as CE3. Just packaged differently. And now we have a CE4 dash, which is, we've added video, HEVC video, and then we're continuing to use the audio from the CE3 profile. This is our processing system at a glance. On the input, we are Spera in the cloud. We have MPEG-2 ProRes, DPX, and IMF MXF source formats. That's what our content providers can delivered to us. Our entire processing workflow is cloud, and output, of course, we've got the various video profiles, and I have a shameless plug for Vanguard Video, who was our early HEVC partner. Key points, it's a distributed architecture. It's elastic, the benefit of the cloud. It is 100% cloud. And we currently run thousands of each C2 instances. That's in our steady state, and again, it's elastic so we can spin up more as we need. This is our encoding V1. This is what we stood up in 2007. It was script files running on servers in a data center. 100% Microsoft, using Microsoft tools, Expression Encoder, some of their command line tools, WMV, WMDRM. The encoding framework was built on AVI Synth and Video for Windows. And it would scale to a few thousand titles. It got us through the first year of streaming. Encoding V2, what we codenamed the Matrix, was stood up in 2009. Some key points here. We moved to EC2. still running Windows, but it was written in Java. Same video framework as our previous. We actually just took that tooling and brought it into the EC2 ecosystem. Still AVI synth and video for Windows. We could scale to tens of thousands of titles. The Matrix platform got us actually all the way into 2012. I'm sorry, 2013. So we were able to actually see a substantial amount of growth on that platform. We added H.264, AAC, DD+, etc. Basically every new format. And Matrix was the production system for all encoding profiles, starting with Vega, which was the BD Live application I talked about last year. That was a 2009 PS3. And then after we stood up Vega, we then moved the Windows processing over to EC2 as well, and then shut down our original system. There are a few limitations to that system that caused us to go back and re-engineer from the ground up. First of all, we have very long encode times, typically 10 to 40 times play time. We had inadequate source inspections, which gave us very loose tolerances in our systems, unreliable duration, play duration, which caused some issues on the clients. And we had very few source problems were detected early. And a source problem is typically a problem in code, so problem sources ended up being bad experience for customers. And a bad experience for a customer. Then we had an inefficiency in the workflow where customer calls customer support who complains, who reproduces, starts escalating through several layers of support, finally gets into video engineering, and finally ends up perhaps back to me. I would download the source and look and say, oh, this transport stream has a big corruption in the middle. We need a new, we need a replacement. And so you have like 10 or 15 people, several weeks in bad customer experience, all tied to a source problem. And also the Matrix just really didn't have the ability to scale sufficiently for the growing business. So where, 10, 15, 20 million customers seemed like a big number in 2008, in retrospect, it seems very small. Our newest platform, which we've appropriately named Reloaded, was fired up in 2013. Some key points of Reloaded: it's all 100% Linux, and we're using FFmpeg as our pipeline. It's designed for infinite scaling. That doesn't mean it scales infinitely, or it can scale infinitely. That simply means that we did not design it with any hindrances to scale. So as the underlying tools continue to scale out, we will scale with them. We now have robust source inspections, parallel video encoding, and the ability to support very large source files, which is an issue I'm going to talk about in a little bit with regards to 4K. Here's a few key points designing for scale. First of all, we need to do thorough inspection of all incoming assets. This is very important. I will talk about this in a few minutes. I've already touched on it briefly. Through the whole system, any issue needs to be detected at the point of failure. And a situation we have with Matrix was often problems, for instance, the bad source would get all the way to the customer and then start working its way back through the system. Very inefficient. Other times a bad source would cause an encode failure. But if you had detected the source problem at the source, you would know what was wrong. When the encode fails, it just fails. Now you have engineers have to download assets and do triaging. The system needs to be robust and failure tolerant. We need to have a progressive model for long processes. This is really important, and I will give you some good examples of this in a bit. We need parallelization where needed, and that would again be long processes. And we need a very highly predictable output. I always, we kind of consider our video farm as a factory. And so whenever we're meeting technical meetings internally, I always talk about like a car assembly line. And imagine if the customer stepped on the brake and found out the brake pads were not good. They're inspecting continuously as that car is moving through the factory, making sure that everything is done properly, and they have very predictable output at every point. Likewise, in a highly scalable production farm, video encoding farm, we need to have that kind of point of view that at every step along the way, we need to make sure what comes out is exactly what was intended, and otherwise to fail it. This is just a simple block diagram of our workflow. We have inspection, encode, packaging, and then we deploy. And I'm going to talk about inspections and encoding. For inspections, the premise is that a predictable encoding system requires good input. So what we do first, we verify the source conforms to delivery specification. We auto-route failures with actionable error messages. So when a studio or post house uploads an asset to us, we have to reject it back to them with very specific errors. Often we would like that tied to a knowledge base, but give them information for correcting it. But they need to understand what the problem is. So we can't give them like an FFmpeg error number. We actually have to give them a good verbal description. MPEG-2 transport stream had packet sync loss at packet number whatever, or that there was a video decode error at frame number whatever, something that they could actually go back and verify on their system. We need to do system layer and decode inspections. We actually fully index the elementary streams of every source coming in, and I'll talk about why in a little bit. And then we have multiple sources of truth model, and I'm going to talk about that again in just a minute. Starting at the system layer inspections, we verify conformance to the relevant system specification. If it's MPEG-2 transport stream, the stream must be conformed to the spec. If it has a non-conformance, we'll reject it. Similar for MP4 and IMF, MXF, other source formats. An example, MPEG-2 transport stream. When it comes in, the first thing we do is a system layer analysis. We look for any sync loss, any continuity issues. We check the timing, buffer, all the STD delay, all the MPEG-2 transport stream parameters. And if any aspect of the file is out of spec, we will reject it back to the content provider with an actionable error message. For MPEG-2 transport stream, for example, they could load that into any third-party analyzer, and they would actually be able to confirm the error at the specific offset exactly how we told them. Then we do decode inspections. We fully decode the source front to back, and there can be no decode errors reported by the decoder, so it has to be 100% correct at the bitstream level. We then do decoded picture analysis on the decoded stream. We do telecine detection. We do not allow sources with converted frame rates. We require every title be delivered at its native frame rate for obvious reasons. We believe that delivers the best experience to the customer. So if we detect a telecine, we'll reject the asset with an appropriate message. We look for commercial black. Very often when we get assets that were set up for broadcast, we have a maximum 2 seconds of commercial black. So often we'll find where they've left in 10 seconds in spots, or they'll have a pattern or something. So we'll detect commercial black and reject. We also do crop detection. And that's not actually a reason for rejection, but when we're inspecting, we look and determine how do we need to crop and mat this, because everything we deliver out is either 16:9 or 4:3 delivered for HDTVs. So that would tell us how we need to process it through our encoding pipeline. And then on the audio side, we're looking for dropout. And actually, one of the biggest issues we have is incorrect channel mapping. So they'll tell us, for example, here's your left-right mix downs. In fact, it's not. It's a side channel. Or even the 5.1, they'll have the channels mixed up so that your dialogue is coming through the LFE or something like that. So we've stood up some audio algorithms where we're now taking our best guess, is the channel mapped correct? And then we have multiple sources of truth. Each of the inspections we do, the system layer, the audio and video decodes, and the indexing, they all produce sample counts. And we require that these sample counts are exactly matched. More often than not, this has been an indication of a problem on our side, not on the source side. In fact, when we first stood up Reloaded and all the new technology, we actually got hit with a lot of these errors. So it was really proving for us, but occasionally there have been some problems on the source side where for one reason or another, the sample counts didn't match. So perhaps the system layer showed, an extra frame, but when you decoded it, that frame was gone. So then we would have to analyze it and figure out where the frame went, report that back to the content provider. I want to talk about the encoding part of our puzzle. We have a new technology we've codenamed MAPLE, which stands for Massively Parallel Encoding. Again, we're in the cloud, and the benefit of the cloud is you have elasticity. You can spin up many instances. So if you're going to design for cloud optimization, everything needs to be designed to be broken up into small pieces that can be distributed amongst a fairly large amount of relatively low power systems. We're typically running EC2 C1 medium, right? So these are not high powered, but by breaking it up into many small pieces, we can get good throughput. So video is chunked across multiple instances. And this actually gives us a progressive model for efficient handling of transient errors. It is one of the problems we have had in the past is occasionally when you're dealing with the I/O in the cloud, occasionally you get an I/O error, which would cause, for example, a long encode to fail, and you'd have to start all over. With the progressive model, these types of transient errors, we would simply you would lose that one small part. So if you've got it broken up into 1-minute chunks, you lose 1 minute of encoding instead of a worst case I'm going to talk about in a few slides. And then we do post-encode verification. When we stood up Maple, one of our concerns was on the development side that we could get some aspects wrong and end up duplicating or dropping frames. That was one problem, so we could end up messing up AV sync actually. And then even worse than that, we were concerned, what if we get the pieces together in the wrong order? So we stood up a set of post-encode inspections that are very efficient, but what we do is we make sure we generate data at the inspection, actually scene change data, and we generate scene change data on the post-encode, and we actually correlate those two, and that's been very reliable indicator of where we've gotten our chunking wrong. And so the benefit of that is when a encode comes out of our new encode process, having gone through this verification, we have about a 5 to 6 nines reliability level of that encode. So we know sometimes we have some false positives that were good, but we've not had any false negatives where a bad encode actually got through to our customers. So this is what it looks like. We have a chunker. The chunker will break it into individual pieces or small pieces and dispatch those out to the individual EC2 instances, which do the encodes. When they're all complete, we'll have an assembler put those pieces back together, and then we run the verification step. Here's a few use cases, Maple in action. Last year, we had a great opportunity for a day after broadcast of a very popular title in the US. I've been told I can't mention the name, but it is a very popular title that might have something to do with drugs. And we had an opportunity to stream that in the United Kingdom the day after. The problem was that we were unable to get the source with much lead time due to the potential for spoilers or things leaking out. The owner was unwilling to give it to us but a day early. But this is actually some of our results. These are 2 episodes. They're each about 45 minutes, and you can see on the side we're running about 3 hours to inspect and encode. Average was about 7 hours, 2.5 hours of which was encoding, and that was encoding in 3-minute chunks. The rest of the time, the 4.5 hours was in inspection, and actually we've substantially improved the inspection time, so that would be cut in half, so now we would be at about 5 hours. And this is all bit rates all the way up to our highest 1080p bit rate. Compared to the Matrix, this same title, 1080p, took 46 hours to encode the 5.8 megabit 1080p. So that's a substantial improvement, and that 46 hours is if it was successful. If for any reason it failed, then you would have to restart that. So if it failed at 45 hours and 55 minutes, then you got to start all over again. A second use case is actually the worst case encode that I've seen in our system in the history of streaming. I've been there actually since 2007 when we started. This was a 4.95 hour title. Can't mention the name, but it was a collection of shorts by one very famous cinematographer. She made shorts, and this was basically her entire life work. It was 4.95 hours. It actually took us 96 hours to encode the 1080p in the Matrix. However, when we finally got that 1080p out, we had over 900 compute hours invested. And there were several reasons. Occasionally, we would get the transient errors I mentioned, occasional I/O errors. Sometimes the instance they get used after a while, they just kind of stop, and you have to restart them. And then also, the Matrix, when we wanted to do a push to fix issues, we would have to bring the whole system down. So taking that long, it was like almost every time it would almost get done, we'd have to kill it because we had some urgent production issue that was on a much higher, more important title. And so we ended up with over 900 hours invested in this one asset before we finally got the HD stream in production. Maple did it in 3 hours. And again, because of the progressive nature, any transient failures along the way or any need to shut down would simply, the state would pick right back up and resume from where it left off. The Maple summary, it's given us the ability to deliver day after broadcast at all bit rates, and actually we've brought this up to 4K. We have very tight system tolerances now. Our inspections require plus or minus 1 frame, and I would say minus. We've never actually been plus 1 frame. But the video coming out of the encoder has to measure plus or minus 1 frame, and the only reason we have that is because we do get interlace content, and depending on the deinterlacing model, occasionally you may lose that last field. And so we allow that 1 frame of tolerance at the end. We have very high confidence in the quality of the encodes. Our progressive model minimizes the impact of transient errors, and we believe that we still have much opportunity to improve the performance. So we're looking at getting that down from 5 hours down to the 1 to 2 hours from the time it lands in Aspera to the time we have streams ready to deliver to the CDNs. The conclusion, Maple is sweet. Now I want to talk about our 4K. As I mentioned, we went live in April with one of our more successful originals, House of Cards, in 4K on the small number of 4K devices that are actually available, that are Netflix ready as well. There will be more coming out over the next month or two, but you can go down to Best Buy today and buy a 4K TV from Samsung that's Netflix ready. If you have sufficient bandwidth, plug it in, you will get to watch House of Cards in 4K. For us, Ultra HD, of course, we all think about 4K and everybody talks about 4K resolution, but we don't really feel like the resolution is the start, and we don't necessarily believe that the really big value is in resolution. Certainly not resolution alone. There's a lot more opportunity that we're really interested in pursuing. Obviously, high frame rate. We're very interested. We've done a lot of testing. We've produced some high frame rate content, and we're very excited about what, for example, 4K 60 versus 4K 30 or 4K 24. The difference in the experience is just phenomenal. We're also very much interested in the wider color gamut of Rec 2020. Still waiting for those devices that can actually display those colors. We're able to see the high frame rate. We're not yet able to see the high colors, but we're looking forward to that. And of course, the high dynamic range. We believe that, from all the demos we've seen and everything, we're very excited about high dynamic range, and we're very interested in a standard emerging that we can then move aggressively to support. There are some challenges we faced when standing up our 4K workflow. First of all, we have emerging standards. HEVC, we were working with HEVC a year and a half ago. The spec was still, the ink wasn't dry on the spec. HDR is not even, there's several competing specs at this point, so it's not yet clear which direction we should go. Early on, we had an issue with bitstream analyzer immaturity, so we're trying to kick the tires and run some tests and start decoding and using HEVC streams. We've always relied on third-party analyzers such as Tektronix or Intera to help us with bitstream problems and trying to figure out if it's a codec, an encode issue or a decode issue. But the tools early were very immature, and so we had limited ability to do bitstream level analysis. There were very few decoders. If you're kicking the tires on an encoder from company A, the last thing you want to do is use company A's decoder to determine whether or not they're producing good streams, because I would say almost every company, their encoder is guaranteed to work with their decoder. But we're more interested in cross compatibility. So we would use the HM or the reference to the extent possible, but we kind of had that issue with very few decoders. We had a tremendous challenge with source files. Our House of Cards, we ingested DPX, runs about 2 terabytes an hour. If you drop it into a zip file, you'll get about 1.8 terabytes an hour, which is a great reduction for us. And I want to talk about working with a 2 terabyte file. This was actually one of the more difficult technical challenges for us, because the EC2 instances we are using do not have anywhere near enough hard drive space to land one of these files. And actually, at the time, things may have changed. The only way you could get 2 terabytes was to get one of the largest, most expensive instances and RAID the drives. So they would have like 400 gig drives. You'd actually have to RAID them all together. Not really something that would have scaled for us or something that we would have been interested in doing. And then even if you did have the hard drive space, downloading 2 terabytes could take 24 hours. And we talked about the transient failures. You could imagine getting a transient error, you know, when you're like 1.79 terabytes into your 1.8 terabyte file and having to start all over. So that does present a difficulty dealing with transient errors. The solution for us, I talked about Maple. The solution here is actually chunked inspections. With chunked inspections, we're able to manage large files efficiently. We're actually able to parallelize the inspection so we can get the scale, cloud scale. That actually gives us a progressive model. I talked about the I/O. So now we have progressive inspections on these large assets as well as progressive encodes. Initially, we stood up the chunked inspections on DPX. We've now extended that to IMF, MXF, and ProRes. I'll talk about these formats a little bit more in a later slide. So we're ingesting and encoding DPX, IMF, and MXF at scale. I'm sorry, DPX, IMF, MXF, and I missed ProRes, and ProRes at scale. So we're inspecting them parallel, we're encoding them parallel. We now have the ability to move 4K assets through our workflow almost as quickly as we can move 2K assets. I say almost because HEVC encode performance is a little bit slower. This is what it looks like, the chunked inspection. Again, very similar to our encoder. We have a chunker up front that dispatches jobs out to each of the inspector jobs or joblets. They'll each take their part, inspect it, and then we pull the results together, and those are stored back up into our system as if they were encoded in a serial manner. So really no difference once you get past that. Let me back up and talk about this. Again, as I mentioned, the parallel inspections now allow, and I talked about our day after broadcast and spending, we actually spend more time inspecting than we spent encoding. Now we've parallelized the inspections for certain file formats. We're actually now able to get inspections down sub 1 hour. We're able to get encodes down sub 1 hour, which means we're looking at about a 2 to 2.5 hour time from landing on the Aspera to being packaged and out ready for deployment to CDNs. I want to talk about our source format roadmap, the sources that we ingest from our content partners. Our current supported formats are MPEG-2 transport stream, Apple ProRes, DPX, and IMF MXF, which is a brand new source for us. MPEG-2 transport stream is very well supported. It's been with us for a long time. I've been working with these files actually for almost 14 years in 2 jobs. But it's not really a format, a file format. MPEG-2 transport is actually a broadcast or a transmission format consisting of a bunch of packets. There really is no file. And so, as I mentioned, some of the problems we were having earlier, a corruption in a QuickTime file, for example, is going to fail as soon as you try to open it up in a QuickTime reader. Corruption in a transport stream actually you would very seldom notice because the entire transport system was designed for robustness. So if you're reading or decoding a transport stream source and you have a big corruption in the middle, loose packet sync, the demuxer is simply going to go into a state. I'm out of sync, I'm out of sync, I'm out of sync. Okay, I'm back in sync. And it's going to start delivering video right back down to the encoder with no idea of what actually happened in the middle. And though broadcast seems to recover well, we've often found that usually when we get through these issues, we'll end up with an AV sync, for example, because we'll lose a little more. Maybe we got a partial video frame, the decoder threw it away, but the audio, because you've lost the PTSs in the pipeline, perhaps you end up out of sync. We are not unable to do MPEG-2 transport stream inspections using our parallel model because you really have to look at it as a sequence of packets and you have no way to know how to break it up. Video quality is not really that great. Most of our MPEG-2 transport streams are MPEG-2 video. We have some that are AVC intra, but in general, we're running about 80 megabits is what we spec for the video. And really, a few years ago, we felt that was very high quality. But today, we're really feeling like that quality is not suitable for the quality that we want to deliver to our customers. Now, we fully support ProRes in our workflow. And this is a very high quality video encoder. And the QuickTime container is a little more robust than Transport Stream. If it fails, it's going to fail bad. It's going to fail early if there's any corruption in the upload. We fully support parallel and progressive processing, both in the inspection and the encode for ProRes, so we can move these through our workflow very quickly, regardless of the resolution. But ProRes is a proprietary format. It's not really spec, so Apple doesn't have any specifications on ProRes. There are third-party tools that have mostly been reverse engineered, and licensing technology from Apple with regards to ProRes is not something they have a normal program for. So for example, if you wanted a ProRes encoder, you either have to use Final Cut Pro or you have to use tools that have typically been reverse engineered, at least to our experience. If anybody knows different, I would like to hear that. But so it's a proprietary format. So that's kind of the problem we have, the concern long term, is we prefer open standards. Now DPX, our original 4Ks were all ingested DPX, is exceedingly high quality, right? And actually it's the highest quality because the images aren't even compressed. We're able to fully implement parallel and progressive processing, so we can actually move these assets through our system fairly quickly in spite of their really, really big size. And we just feel that the size of DPX makes it unwieldy for us, right? It may make sense if you're a content owner and you're archiving and you want to archive in raw format, but for us, it really just doesn't make sense. Given that we're 2 terabytes an hour and we have S3 has a 5 terabyte object size limit, we also would have a duration limit of about 2.5 hours, and that's for a title, unless that's actually zipped. Unless we implemented a different workflow that ingested it as frames, individual frames, and we discussed that, but somehow in ingesting like 20,000 or 100,000 frames individually seemed like a very difficult proposition that would be very troublesome and error prone. So we don't really feel that DPX is practical for scale because of these reasons. Also, one of our 4K assets in DPX had a few frames that were bad shortly before launch. And we had to re-ingest those after they were fixed. And 1.8 terabytes, I mean, basically it was a very last-minute heroics just try to get those systems live, those assets live. And though we could architect a model for replacing frames in DPX, we feel again that would be very error-prone and difficult for our content providers to build out for. IMF-MXF, the JPEG 2000 profile, is very high quality again. Of course, dependent on how you choose to compress the video, you can go lossless JPEG, or you can actually go fairly high compression. We would steer our partners into either lossless or compressed, but at a very high quality level. We fully support parallel and progressive processing of IMF-MXF. It's an emerging standard. Still has a long ways to go, but it gives us the ability to deliver incremental revisions and localized playlists. So we could actually receive an IMF-MXF asset that covers the entire world, all regions, with different CPLs for each area. And as we license that area, we could then just we run it through the encoder to actually produce that localized encode. Also the ability, if they have to do a fix, going back to that where they had to replace like 8 frames, rather than delivering the whole asset, they would just give us a new IMF-MXF that would reference the old. So you actually have that ability to have a change history, much like source control. So we're very excited about IMF-MXF. We stood up our first IMF-MXF assets, or actually we ingested them in February 2014. We've now got about 70 assets, 4K IMF-MXFs we've ingested and processed in our system. A summary of this: MPEG-2 transport stream is legacy. It's a very good, it's been a very faithful model, but we don't feel it's suitable for UHD, and it really don't feel it's suitable for the scale that we're looking to achieve over the next 5 years. ProRes is very high quality. It can meet the scaling requirements. We're only concerned there is it's proprietary and not, Apple's not real public about the specifics. DPX is unwieldy, so we don't really feel like that's going to be a good source model for us. It's the opinion of Netflix on the source side, mind you. This is not the client side, IMF, MXF is the future. To that end, we're investing heavily in support around IMF, MXF. It's currently, we've messaged out to our content providers that this is the preferred format. So for those that have the workflow tooling able to support, we are asking that they deliver IMF, MXF. For those that don't, we're working with them to get that on their roadmap. There may be a time in the future, perhaps a couple years, where we will only accept IMF, MXF input. One little point I want to mention on our support, this is a very large spec, lots of features and functionality. We've only implemented the very basic. So it's a single audio essence, single video essence. The playlist, it just plays from beginning to end, so no edits. But we're now iterating through adding the ability to deliver incremental revisions and the other functions or features that we feel are very important. I'm going to close out with some random thoughts, starting with HEVC. And for anybody who's in the codec business, this is, well, anyway. We've actually evaluated many HEVC codecs, as you might imagine. Many technology vendors would like to sign deals with Netflix. So we've kicked the tires on a lot of them. What we're seeing so far is not the efficiency gain that's being claimed in all the press. So we're hearing 30, 40, 50%. Our encoder delivers 30, 40, 50%. We're not seeing that. I'm not saying it's not being achieved. I'm merely saying that we're not seeing it. But I will say that we're running a very different model than most of the codec vendors, because most of the codecs are being rolled out initially for real-time encoding, and so they're being compared to real-time, and so they may be seeing those efficiency gains in a model that we're not using. We're doing non-real-time, and our reference is X264, which is a very high-quality H.264. So right now, we're not seeing the efficiency. What we're seeing is about the same quality at about the same bits, with a much longer encode time, getting up in one order of magnitude. But this is also very early in the HEVC life cycle. So, I mean, if we go back to 2002, I think, when H.264 rolled out, I mean, you consider how long it took to produce an encode back then and the quality. You know, and X264 was like 2008, 2009 before it really made that last major step in quality. And so, I mean, that was 6, 8 years into the life. And we believe that what we're seeing with HEVC is that it's a much accelerated development cycle. And so, though this is what we're seeing, these are not our expectations. In 2 years, we expect 20 to 30% efficiency versus X264. And again, this is efficiency in our systems using our sources, right? Because we measure efficiency in the aggregate, not on this file is 30%, but these 1,000 files are showing 30% on average. So we're expecting to see 20 to 30% average efficiency in a select set of our content library versus X264 in non-real-time mode. We're expecting the encode time to drop down near X264, though we don't ever expect them to ever be able to encode at the same speed for the same quality. We expect HEVC to be substantially faster than it is now. And Netflix is actually very excited about HEVC. Almost all of our dev is around HEVC now. We're making very little investment in H.264. We feel that we've got a good solution for what's now our legacy. We still have new clients coming out that are H.264, but very quickly as the UHD 4K and HEVC devices roll out, the CE3 H.264 is going to pretty much stop, and all of our innovation is going to be shifting then to HEVC. And so we're very excited about HEVC. We're making a lot of investments in the technology. We're engaging with a lot of HEVC partners. So we're not pessimistic. I'm telling you what we see, but also what we expect to see. Here's a little random trivia I'm going to close out with, just some stuff on Netflix. When we transitioned to Reloaded in the summer of 2013, we had to re-encode every single AAC audio and Dolby Digital asset due to some licensing changes around some old codecs we were using. This was probably one of the most painful experiences of my life, mainly because we have sources that we ingested in 2007 back on our old scripted system. And so it wasn't the new stuff that was giving us headaches, it was the old assets. But we actually had to re-encode and replace on-site every single AAC audio. So basically, it's audio for every asset we have deployed. That actually took us a few months. We currently have 50 plus encodes per video, and by encodes I don't mean literally elementary streams. That's a combination of codecs, packaging, and bit rates. Right? So as I mentioned with my profile slide, we use the same encode for CE3, iOS 1, and iOS 2. So you add up all those bit rates and packages, we end up at about 50 plus, a little more than 50 per video. Currently, our cloud processing is all C1 medium, and we have no GPU acceleration in our system. We kicked the tires on the GPU accelerated instances a few years ago, but the price versus performance is just not there. If it's 10 times more expensive, but 3 times as fast, that doesn't scale. And also, a key part about Netflix with regards to video encoding is we never trade quality for performance. Because the nature of our business, unlike the keynote this morning where they got to get everything out very quickly, the nature of our business is we tend to receive assets, with the exception of day after broadcast, well ahead of time. We often have months of lead time. And so we always want to have the highest streaming quality possible for any given bit rate. So we're never interested in faster. And actually, we're seldom interested in smaller. So for instance, we have our maximum 1080p is 5.8 megabits. Now, we're not interested in holding that quality and reducing it to save bits, unless, for example, it was animated and you ran out of information at 3 megabits, then we might be interested. But in general, if the quality versus bit rate curve has not flattened out at 5.8, we have no interest in reducing that bit rate down lower. We would prefer to deliver the 5.8 to the customer to get them the best quality possible. In fact, we might even talk about going to higher bit rates if there's an opportunity. If the source has sufficient value, sufficient information, where 1080 might look better at 8, we might consider even streaming at 8, though we haven't made that decision yet. Our 4K DPX workflow was stood up in about 2 months. We started in October. It was actually supposed to be August, but all that audio set us back a couple months. So we started in October. We actually had it working by the end of the year, and we actually had our initial 4K titles all ready for launch by January 1st. Our initial IMF MXF workflow was also stood up in about 2 months. And if anybody remembers from last year, our original iPad application was stood up in about 2 months as well. So there seems to be a 60-day wall for Netflix where there's not much big we can do faster than 60 days, but we can do a lot in 60 days. With that, I'm going to open it up for questions, and we have a good bit of time. So we'll go as long as we need to. Yes, sir.
On the 4K stuff, since you're not seeing the efficiency, are the file sizes not as small as they might have been compared to 2K files? And how is there a recommendation or on how consumers are going to get those fat files into their homes? And what are the FCC fast lanes? How is this affecting how consumers are getting these fat 4K files into their homes?
Okay, so let me try to summarize the questions. We don't have a microphone here. With regards to 4K, you want to know about the bit rates that we're producing?
No. How big are the file sizes themselves compared to the 2K file, and how fat are they in comparison?
And efficiency. Okay, and you
home?
also mentioned efficiency. Okay, so on the 4K, I'll tell you what we're producing right now. We're starting around 8 meg and going to 16. We can't really give you an efficiency number because we're doing main 10 HEVC, and we don't really have an appropriate comparison in X264. And we've only our X264 comparisons end at 1080p, and we extrapolate it out for 4K. But by the numbers, the HEVC codecs do seem to be doing better in terms of efficiency at 4K. At 1080p and below, they seem to be about equivalent. But again, we don't have the 4K a reference. We actually don't have like an X264 reference for 4K. As far as customers getting those streams, you need 12 to 16 megabits average, I would suppose. 20 would be preferred. If you guys don't mind, I'm going to take a quick picture while I still have a crowd here. The last presentation, there was like 6 people in the room, so I was a little worried, but I can show my boss, say, look how much better I did than YouTube. I'm sorry, did I answer all your questions?
Well, I mean, who is getting the 20? Are you suggesting, are there particular ISPs now that are better equipped to handle those files?
No, I can't. Yeah, I can't. That's not my line of expertise. I'm an encoding nerd, so I'm all about video, and I really couldn't answer the specific questions about ISPs. I can say if you have a throughput of 20 megabits, certainly if your ISP uses Open Connect, but even some of the others, perhaps I couldn't answer, but perhaps others. There's so few devices, 4K devices out that we don't even have the metrics or the ability to get metrics on that yet. Yes, sir.
Kind of piggyback on that question. So if I watch a 2-hour 4K broadcast, how much data am I downloading? Am I going to hit
16 megabits a second.
So am I going to hit my monthly cap?
It depends on your cap. It's 3,600 seconds an hour times 16 megabits, which would be about 2 megabytes. Yes, sir.
Plus encode profiles, and you just threw a whole lot of water on the whole HEVC thing. I'm just wondering, do you see going from 264 to transitioning to HEVC, do you see a time when Netflix will need to support HEVC and H.264 support in mid-chunk switches for mobile and desktop devices?
Okay, so the question, if I can summarize, is we have H.264, we're now setting up HEVC, and do we anticipate ever being able to do adaptive switching across from one codec to the other? The answer to that is no. For our CE4 HEVC devices, they do have a compliance cert requirement that they're able to play any CE3 H.264 dash stream. So, but they're going to play A or B. We're never going to give them A and B. And that's very important because it would be very difficult for a decoder to have been initialized for H.264, but then to seamlessly switch over to HEVC. So when they do a movie request, they'll say, I can do H.264 and I can do HEVC. We'll return them back one set of streams. It will be A or B, never A and B. That allows us to roll out HEVC. Right now we didn't re-encode our entire library in HEVC. We did our 4K and some other assets we feel would benefit from HEVC, and the rest of the library is just the devices continue to play off the CE3 streams. Does that answer your question?
So you anticipate never having to switch mid-chunk between HEVC and H.264 in any circumstance?
I would never say never, but I would doubt very seriously that we would ever put a requirement on our device partners that they must be able to seamlessly switch from AVC to HEVC. I think that would be a very difficult requirement for a codec implementation. Yes, sir.
I noticed that you talked about that you currently have about 50 encoding profiles, and if I remember from previous Netflix presentations, I've seen the number be much higher, like around 120 encodings that you have to do. Can you talk a little bit about the efficiency?
So the question is, I said we have more than 50.
Okay.
You said you've seen in other talks 120. That 120 number pops up a lot, but it's kind of something that's outside of Netflix. It's not a number we've given inside. It's probably a little big. More than 50 is a little more accurate because if it was more than 80, I would have said more than 80. But again, that's the point I want to make is when you add up, for instance, for VC1, we do 3 bit rates, or 4 bit rates if it's an HD source. And we do that twice for the video. We do the 4 streams for CE1. We do the 4 video for CE2 plus 2 audio for CE2. So just for the legacy devices there, we've got 8, 10 streams, right? You move into CE3, now we've got baseline for the legacy mobiles, we've got main profile, and we've got bit rates running from 100K all the way up to 5.8 megabits. So then you've got audio, 2 bit rates AAC, you've got Dolby Digital Plus, and you've got OGG Vorbis, right? So then you start adding all those up, and plus the iOS, the ones that are MUX for iOS. When you add all those up, the bit rates plus the package combinations, then you get up in the more than 50, but I would say less than 120. I'm going to go back this way first. Yes, sir.
A question about how you view the proliferation differences between VP9 and HEVC. For you guys, is VP9 basically just not out of the question?
So the question is, how do we view the proliferation difference between VP9 and HEVC? So Netflix doesn't produce hardware. We almost did, and we got out of that business in 2007, and our model has been to stream to the world rather than having a box. And so we implement what the world is asking for. And the device vendors at this point, all the TV makers at least, and set-top box, they're all asking for HEVC. So we never did VP8, and we probably, I would at this point say we never will. We're not, VP9 is not currently on our roadmap, but I will not say that we never will, because where there's a business opportunity and we feel that there's value, then we would pursue that. But at this point, it's HEVC is what everybody's asking for. The mobile devices, even their roadmaps, everybody's talking about HEVC. Does that answer your question?
Yeah, sure.
I'll get to you in just a minute. Yes, sir.
Hi, Dan. Bob Wilson from Sonova. Great chat. Curious, two questions. One, if you can tell us how many Netflix customers actually receive the content as an ABR stream, adaptive bitrate stream, if that's something you guys can talk about. And then secondly, to your point about better user experience, I think is you're just not going to trade that off. Would you trade lower bits for higher resolution so that you could deliver a higher resolution to the user? Would you view that as a better user experience, or is it primarily a bit rate that you're talking
Okay, so let's start with your first question, talking about adaptive bit streaming. So the generations of devices, CE1 is the only device family we have that does not support adaptive bitrate streaming. So if you're on a Roku One or some of the really old Blu-ray players, mostly, I'm not sure, there may be one or two connected TVs would be the earliest. Then you're on CE1, you don't have adaptive streaming. And you can always tell when you start if you actually see the quality bars at the middle when it's buffering, telling you got like 1 bar, 2 bars, 3 bars. That's your clue. You start at CE2, which is almost all of the connected TVs and the newer Blu-ray players, moving all the way through all the new devices, everything is adaptive. So I don't have the numbers. There's still a sizable number of people, much more than, actually for me and my team, there's nothing we'd like more than to shut down the Windows cloud instances and turn off those old Microsoft tools. But we've got a substantial number of customers that are still happy with that service, and so we have to produce those streams for them. Your second question, I'm sorry if you could repeat that.
Yeah, so in the second question, user experience is clearly what you're after. Would you trade off, would you accept lower bit rate if you could get higher resolution delivered to the end user? Or is bitrate your primary determining factor for what that user experience is?
So we're doing a lot of investigation around bit rates and resolutions. And in reality, there's not a one-size-fits-all. And I'll give you an extreme case, and that's animation, and even more particular, anime. Anime, though we're currently delivering 1080p anime at 5.8 megabits, in reality, we could be 1080p at about 1.2 megabits. And actually, if you add more bits beyond that, the quality, you'll see the quality goes flat, right? Other assets, we're nowhere near. We're at 1080p at 5.8 when we could actually have a higher quality. Well, I don't know about 5.8, but we may go up to 1080p around 3.8, but we may find that our quality would have been better served if we would have held 720. So it's about getting the information and the user perception of quality. Users don't necessarily perceive more pixels as more quality. Right? What they tend to focus on is loss of clarity, motion artifacts, things like that, particularly motion artifacts and blocking. And so I would suggest that you'd almost be better delivering 720p, a very clear picture, than 1080p with blocking. But that ends up being a per title. And so ultimately what we'd like to do is have that decision made at a per title level, not just a one-size-fits-all recipe. Yes, sir?
This is sort of related to that. You mentioned 5.8 meg for the 1080p, and you mentioned nominally 15 meg for the 4K. Are you producing any bit rates, or do you see any need to produce any intermediate bit rates between the 5.8 and the 15, and any intermediate resolutions?
So yes, we do have intermediate bit rates. For example, 720p starts at 2350 currently and 3000. 1080p starts at 3850, and then 4300 goes to 5.8. And then 4K also starts at 8 and walks up to 16 in 4 steps, 8, 10, 12, and 16. With regards to intermediate resolutions, we're actually kicking the tires on, what was it? It would be QHD. It's 2 times, it's 720p double. So it's 1440 by 2560 as an intermediate between 1080p and you know, we've talked about it as a big step from 1080p to 4K, but we don't just want to make up some resolution. So there actually is a QHD resolution, which is 720p doubled. So that kind of gets us perhaps not as high as we would have wanted, but it's a nice intermediate. Now, we're not officially supporting that. We're simply kicking the tires on it. Yes, sir.
So you mentioned measuring the quality. Can you talk about how you actually do the process for measuring quality for encodes, and do those same tools work with 4K?
Process for measuring quality. Actually, I could be up here for about 2 hours talking about that. In the olden days, our process consisted of 2 monitors, and we all stood around and said, wow, I think that one looks better. No, I think that one looks better. And for a company, you have to understand, I mean, Netflix is a data-driven company. Every decision we make is driven by data. And it drives us nuts that we're making quality decisions with everybody standing around looking, and we've often gotten it wrong. Right? We've gotten some quality decisions wrong. And so we've been working very hard to bring science into this. The first thing we did, and it's only an iterative step, but we licensed the Tektronix Perceptual Quality Analyzer, which we feel is, it's not perfect, but it's a useful tool for measuring perceptual quality as opposed to PSNR and SSIM, which really don't necessarily correlate to user experience directly. And so now when we evaluate quality of a recipe change or a third-party codec, we'll take our reference encodes, compare them to X264 using the PQA tool, where a lower score is actually higher quality. And that was actually what we used in working on our HEVC recipes, because we wanted to have the initial launch for 4K, for the sub 4K resolutions, was the quality could not be worse than X264. So we wanted to find, but we were trying to get the encodes to move through the system, so we wanted to find the lowest quality setting that would allow us to meet X264 quality, but still have a little more performance in the system. So we used the Tektronix Perceptual Quality Analyzer. But we're also doing internal research around better ways to measure quality. We funded some university level research. There'll be some papers coming out in the next year. We're very excited about the work they're doing around perceptual quality. It all involves having lots of people watch videos and score qualities, and then developing tools that can try to meet those metrics. It's really what it's all about. And so that's where we really see the opportunity, and hopefully we're working hard to push that envelope going forward, because we feel like that's a big missing piece of the ability to really drive video quality at scale. So, I mean, the video quality nirvana for me would be able to make a recipe change and run it against 1,000 assets and have metrics driven and return back an average score. And in that case, if we were able to move the mean 2 or 3 or 5%, I mean, that's a huge difference, right? When you're talking about 1,000 or 10,000 titles, and you do that in coding, you've actually moved the mean 5%. That's huge. So we're working on kind of quality at scale, and we'll be talking about that more. Perhaps I'll have more to talk about next year. Yes, sir.
Can you tell us about audio encoding? How do you deal with audio? Is it chunking like the video?
So the question is, how do we deal with audio encoding? Specifically, is it chunked like video? No, video is discrete, really lends itself to chunked processing. Audio, first of all, the audio encoding is much faster. And also we would be concerned about chunking it and getting those pieces together properly. Now, I say that, but I'm going to go back and change what I just said. But first I want to say, what we have stood up in our new system is an intermediate audio. For instance, we still have legacy instances for the Windows encodes, and we don't, for example, want to bring IMF MXF support onto a Windows platform. So the first thing we do with a source is we produce an intermediate audio. It's a lossless. We're using lossless FLAC. And then that lossless FLAC serves as a source for all of the encodes we do. Now, those files are, you know, when we're dealing with assets that are hundreds of gigabytes, having an audio file that's 8 or 10 gigabytes moving that down and encoding it, we're talking about minutes. And so it's really not a blocker. And when I say about chunking, the formats, for example, ProRes has indexed audio. The file, it is indexed. And so we do end up bringing that down in chunks. Although we're doing it all on one instance, we're never really looking to parallelize that. But we are bringing it down in pieces and then encoding it in pieces. But that's because the container gives you a very nice index to each piece, and you can assume you have continuity between those sample boundaries. Yes, sir?
Am I correct in understanding that the chunker divides the video into time segments as it processes?
Yeah. For example, video typically might be a 1 or 3 minute. I mean, we've done testing all the way down to, because we have a fixed 2-second chunk size for adaptive streaming. We've brought it all the way down to 2 seconds, but we felt like having 1,800 servers running, and encode in a matter of seconds. I mean, the complexity of managing that versus the payoff for us, for our business model, at the time didn't make sense. But if we start looking at like scenarios where we needed to do near real time, then we might actually then just take our chunk size down very small.
So my question was really, have you noticed quality differences around the boundaries of the chunks?
No, what we've noticed, first of all, we running pre-processing, we can actually configure the codec for each chunk so that we don't have those quality hits. But what we've noticed, if your chunk size gets larger, then you don't really have to concern yourself so much about that. If you plot the quality as your chunks are getting, and the bit distribution as your chunks are getting smaller, you might imagine the bit rate distribution starts closing in very quickly. But larger chunks, which is what we're currently using, so we actually have two models. One is we do a pre-analysis, and then we do allocation specifically. The second one was we just use large enough chunks so that we don't have that. And in our quality metrics, we've not noticed any quality hits. Yes, sir.
Are these inspections after you finish your encoding, and do you do also inspections on the end client devices?
The client does some, and I'm not a client developer, but I do know they do some checks. Right, they make sure that the assets are all the same frame rate, that their lengths are conformed and such like that. I can't speak to that specifically because I don't work on that team, but I know they do some checks just to they have a reasonable confidence level when they press play or they start playing, it's actually going to play successfully.
But nothing in terms of the video quality aspects that you're doing at the encoder level. Let's say your team signs off saying that, okay, very good to go now.
The client manages bit rate. It simply manages a bit rate to try to keep the buffer full. It'll maximize the potential quality, assuming that the higher bit rates are higher quality. And our job is to make sure that the higher bit rates are actually higher quality. Yes, sir.
So you mentioned using Linux and FFmpeg. So is your entire process of the chunking and the encoding of those chunks and then compiling everything back together, is that all handled with open source tools?
No, the FFmpeg is our video frame serving pipeline, right? It's I guess would be considered a linear frame serving pipeline. It doesn't really have frame accuracy. So we take a chunk and go from beginning to end, trimming front and back as necessary. And that's simply decoding. The encoders are all FFmpeg plugins. So we would then, for instance, our HEVC encoder, our partner delivered it to us as an FFmpeg plugin. So we simply run the recipes around cropping, trimming, etc. Those are all in FFmpeg, and then it pushes decoded process frames through the encoder. You have the encode out, coming as an elementary stream, the individual chunks. Now the code to put that all together, those are not open source. That's in Java tools we've written internally. We've had conversations about open sourcing everything that we've done, but it's the only concern is that we're not convinced it's quality enough, the code, that we'd want to go back and make sure it was pretty before we put our names on it.
Are you actually chunking the video into pieces, or are you using FFmpeg as a frame server?
No, we chunk it. So we index it. I mentioned when we inspect, we index. That tells us that we want to start from frame n to frame n plus 10,000. We know the offsets, and we pull them down. In the case of ProRes, we actually pull down the individual frames and store them as individual files, and then push those through FFmpeg, kind of like a sequence of images, because we have a licensed, authorized ProRes decoder library, and we implemented like an image decoder model. So, but yeah, so we always pull just for each chunk in code, we only pull down the part of the source that we need, which is really important for those 2 terabyte DPX files. More questions? Great, thank you all very much.